Dumping a 50,000 line project folder into ChatGPT burns $10 and crashes your window instantly. Welcome to the Freshers, where we break down complex technology into clear engineering mental models. Raw large language models are prediction engines designed to guess the next word in a sequence. They operate using a context window, which is the exact limit of active text memory available. Imagine dumping a massive truckload of loose timber straight onto a single wooden job site tray. The heavy wooden boards immediately spill onto the floor, scattering critical building pieces everywhere. That exact structural memory overload is called a raw context bottleneck. When your prompt exceeds memory limits, the model either truncates data or forgets early rules entirely. Cursor, Claude Code, Windsurf, and Aider look like totally different software tools on your desktop. Underneath the interface, every single system relies on the exact same four-stage backend engine. A codebase folder is a massive binder containing thousands of nested source files and configuration scripts for the application. Instead of dumping raw binders onto a bare desk, we set up 4 specialized job site stations. We assemble a sitemap desk, a material runner tray, a power tool belt, and an inspection clipboard. Together, these stations control what information reaches the worker desk at any given moment. How do tools edit huge code bases without reading everything? Every modern assistant relies on this exact 4-stage pipeline. They route instructions through this outer line to keep active context clean and affordable. Raw file dumping fails, so the engine must build a structural map of the workspace before reading a single line. Stage 1 powers repository intelligence, starting with the sitemap desk on our contractor job site. Plain text search breaks down because it cannot distinguish between defining a function and calling that function later. To fix this, a specialized parser named TreeSitter scans source files into an abstract syntax tree. An abstract syntax tree is a concrete structural diagram that groups raw code into functions, variables, and import nodes. It ignores decorative formatting like white space to highlight how components connect across files. TreeSitter parses 100,000 lines of code across 40 programming languages in 15 milliseconds. This blueprint scanner operates in less than a blink. Once TreeSitter diagrams individual files, the sitemap desk builds a global repository map. A repository map is a condensed architectural summary showing key file exports, class definitions, and interfile dependencies. Instead of feeding 50,000 raw lines into context, the system condenses the codebase into a 1,000 token outline. The system runs PageRank algorithms on code symbol graphs to prioritize central hub functions across project folders. This gives the language model a bird's-eye architectural view while consuming under 2% of token capacity. So the job site sitemap desk holds a complete master directory now. However, it still cannot pull specific code lines to answer a targeted bug fix request. That is why Stage 2 installs precision retrieval to fetch exact project snippets. A sitemap shows where rooms sit, but you still need to pull exact materials without overloading the tray. Stage 2 powers context retrieval, placing a material runner tray right next to our job site workbench. Plain keyword search finds exact terms like error codes, but fails completely on vague conceptual requests. Semantic vector search calculates math distance between numeric embeddings to capture meaning, but misses exact variable names. Hybrid retrieval merges BM25 keyword matching with vector search to pull the top 4 relevant code chunks. Context packing then strips unused comments and imported functions to fit strictly inside token budget limits. So the runner tray holds precisely trimmed code snippets now. Yet the model remains a passive advisor that cannot touch disk files directly. That brings us to Stage 3 for active tool execution. Packed context is useless if the AI model remains a passive text generator with no physical hands. Stage 3 activates tool execution by equipping our job site worker with a universal power tool belt. Large language models generate string tokens in the cloud, but cannot natively interact with local operating systems. An application programming interface, or API, provides standardized rules for two separate software programs to communicate. Anthropic built the Model Context Protocol, or MCP, to standardize tool calls. How does a cloud text predictor safely run commands on local hardware? When the model needs a file, it emits a structured JSON command specifying the target file path. Local software runs that tool call and returns file contents into memory. This standardized bridge gives isolated models virtual hands to work on local drives. With MCP tool connections active, the job site worker can execute multi-step edits across several project files. Instead of rewriting a huge file for a tiny fix, the agent uses search and replace diffs. A diff specifies exact lines to remove and exact lines to insert without touching surrounding code. The system operates inside a React framework, alternating between reasoning thoughts and taking tool action steps. The agent thinks, edits line 20 in authentication code, observes the result, and modifies caller files in sequence. So the tool belt allows surgical file edits across the project workspace now. But the assistant still has no idea whether those edited files actually compile or break the build. That gap requires Stage 4 automated verification to test the new code. Applying file diffs blindly leaves broken code unless an active inspector runs live tests on the workspace. Stage 4 introduces automated verification by installing an inspection station equipped with a terminal execution sandbox. A terminal sandbox is a managed subshell environment where the AI executes build tools, linters, and compilers. The assistant issues command line instructions like npm test or pest to validate modified project logic. The local sandbox captures standard output and standard error text streams returned by the underlying operating system. Like a job site test rig, this sandbox strains new wall panels under stress before final installation. Raw terminal logs provide ground truth diagnostic data directly into the active memory context. It verifies that code executes correctly without requiring human manual command typing. Earlier we saw how React loops apply diff patches, but first drafts fail up to 30% of the time. Automated verification catches syntax errors, broken imports, and type mismatches immediately using background type checkers. When a compiler flags an error, the traceback output is formatted and fed straight back into model memory. This initiates a self-correction feedback loop where the assistant analyzes the error log and generates a secondary repair patch. Like a safety inspector rechecking a misaligned beam on the job site, the model retries until tests turn green. So the inspection clipboard catches broken edits and guides self-correction loops automatically now. But unchecked feedback cycles risk burning API budgets or corrupting files if tests fail continuously. That risk requires safety nets and Git version control to protect the workspace. Continuous automated execution requires strong safety rails against file corruption and unexpected token cost spikes. To protect your project folder, AI assistants integrate directly with Git version control. Git creates an automated rollback safety net by taking isolated code snapshots before every agent edit pass. If an agentic loop runs 20 cycles and fails, running git reset restores working files instantly. Recall how our stage 1 repo map condensed symbols to preserve active memory tokens earlier. System design always involves sharp engineering trade-offs between indexing speed, context volume, and API costs. Full AST dependency parsing takes higher memory upfront, but prevents silent runtime failures across multi-file refactors. Aggressive context pruning lowers token cost significantly, but risks dropping subtle edge case details during retrieval. We open this video by establishing that all AI coding assistants wrap standard models inside a 4-stage pipeline. Every prompt is governed by system prompt instructions that enforce developer persona rules and structured output formats. A system prompt sets base behavior, mandating unified diff output syntax, and instructing the model when to execute tools. Our job site workbench is now fully operational with site mapping, precision retrieval, tool execution, and automated inspection. Next time your AI assistant gets stuck, check its active context window or inspect terminal error tracebacks directly. You now hold the exact blueprint to control, prompt, and master any AI coding tool you choose. That wraps up our architecture deep dive for today. Like, follow, and subscribe for more, and comment below what topic you want us to break down next.